Okay, so let's start talking about this insurance assignment. Um, let's start with the conversion factors. There's two that you should know. First of all, you should know 180 degrees is the same as pi radians or half a revolution. And also that 360 degrees is the same as 2 pi radians or 1 complete revolution. Here are the formulas for arc length and area of a sector in degrees. Those four formulas will help you, but they won't necessarily answer the questions. Think about the problems that we had from the homework quiz or for the take-home quiz, where essentially, if I was completing more than one revolution, then I would obviously, and I was thinking about, for example, how far a horse on a Ferris wheel would go if the Ferris wheel completes, 7 revolutions every minute and the ride lasts for 4 minutes. You wouldn't really want to use these formulas necessarily. What you would want to do is find the circumference of the circle and then multiply by the number of revolutions, then multiply by the number of minutes. So these formulas will help you, but they're not necessarily going to solve every problem that you're going to be given. Okay, so the next thing we want to talk about is the unit circle and what that entails. And this picture you've seen how many times now? Really you'll want that picture and what that represents in the unit circle. So we know that if we rotate the point 10 by theta degrees or radians, the x-coordinate is the cosine of theta, the y-coordinate is the sine of theta, and the slope of the terminal ray, so in other words the slope of that right there, is the tangent of theta. We found these by just using SOHCAHTOA. The sine was the opposite over the hypotenuse, cosine adjacent over hypotenuse, and the tangent was the opposite over the adjacent. So that'll help you while you're trying to solve some different problems. So the first of the identities that we talked about was the Pythagorean identity. And we started with the Pythagorean identity, and we used it to help us find other trigonometric ratios. So, for example, if I knew that the cosine of theta was 1/4, I could use the Pythagorean identity to find out what the sine of theta was, and if I knew what the sine and the cosine were, I could use those both to find out what the tangent of the angle is. So we can use this trigonometric identity, the Pythagorean identity, to find the other trig ratios when you're given one of the trigonometric ratios. Okay, so we had two special right triangles that we used to fill out the unit circle. We had a 30, 60, 90 right triangle and the 45, 45, 90 right triangle. We let the hypotenuse of each one be equal to 1. And we solved for the missing sides. So in the 45, 45, 90, the sides were the square root of 2 over 2, and those helped me fill out the coordinates for multiples of 45 degrees in the unit circle. And then we used the 30, 60, 90 right triangle to fill out the coordinates for multiples of 30 degrees. Its side lengths were the square root of 3 over 2 and 1/2, where the square root of 3 over 2 was the side opposite the 60-degree angle, and 1/2 was the side opposite the 30-degree angle. And both can be used. I know I said the 30, 60, 90 can be used to find coordinates, but so can the 45, 45, 90 triangle. The reciprocal trig functions. This was our last topic. So they're the reciprocals of sine, cosine, and tangent, the cosecant, the secant, and the cotangent. I know it's confusing that the cosecant, yes, it would be great it'd be so easy to remember if the secant was the reciprocal of sine and the cosecant was the reciprocal of cosine, but they are not. The cosecant is the reciprocal of the sine, and the secant is the reciprocal of cosine. So we do have to know how to find the exact values for secant, cosecant, and cotangent. So I give you an example of this here. So if I wanted to know the cosecant of 30 degrees, this would be 1 over the sine of 30 degrees. I know the sine of 30 degrees is 1/2, so essentially I'm finding the reciprocal of 1/2. 1 over 1/2 is essentially what's the reciprocal of the denominator, and the reciprocal is obviously 2 over 1. So that's an example of how you can find the exact values of cosecant, secant, and cotangent, which you will have to do for your test. Okay, the last thing would be the unit circle theorem. So the first unit circle theorem, other than the Pythagorean identity, the first one we talked about was the opposites theorem. This was a reflection over the x-axis. When you reflect over the x-axis, when I compare theta to negative theta, it is a reflection over the x-axis. And the x-coordinate essentially stays the same, but the y-coordinates are opposite. So the y-coordinate under a rotation of negative theta is opposite to the y-coordinate under a rotation of theta. And so are the slopes. The slopes end up being opposite. So in the picture at the bottom, if you look at our picture here, here is the original theta, and this would be a rotation of negative theta. We can see the reflection over the x-axis. The x-coordinates stay the same, the y-coordinates are opposite. This one has a positive slope, this one has a negative slope, so we can see those relationships. The supplements theorem. This is one of the ones that is tricky. So we have the cosine of pi minus theta is equal to the opposite of the cosine of theta. So those are the x-coordinates. This was a reflection over the y-axis, so when you reflect over the y-axis, the x-coordinates are opposite. The y-coordinates stay the same, and the slopes will end up being opposite one another. So if we look back down again, we can see our original rotation. Its supplement would be going to pi and then going back the original rotation. So imagine going to pi and then going back theta. You can see the relationship, their reflections over the y-axis. So the x-coordinates are opposite, the slopes are opposite, but the y-coordinates are the same. Then we have the complements theorem. This is probably the hardest one to see. The complements theorem is a reflection over the line y equals x. So if your original point is x comma y, it becomes the point y comma x under a rotation of pi over 2 minus theta. So if our original angle is theta, imagine going to 90 degrees and then going back that original angle. So we can see that's theta, pi over 2 minus theta, start at pi over 2, go back the same angle measure. So from this we can say that yes, the x and the y's are switched, so we can look at when we reflect over the line y equals x, the point xy essentially turns into the point yx. So the cosine, the x-coordinate under a complementary rotation, is the same as the y-coordinate under a under the original rotation. The y-coordinate under a complementary rotation is the same as the x-coordinate under the original rotation. I forgot to put the tangent on there, and you will need to know that. The tangent of pi over 2 minus theta is the same as the reciprocal of the original tangent. And if you think about it, that's actually the cotangent as well. So the tangent of pi over 2 minus theta is the same as the cotangent of theta. So they would have reciprocal slopes of one another. Their slopes would be reciprocals. The last one is one of the easiest ones to see, is the half-turn theorem. So if this is our original rotation, a half turn from that original rotation would yield this point down here, we can see that the x coordinate and the y coordinate are both opposite one another, but the slopes would end up being the same. So look at them. If you look, they are on the same line, so we can see the slopes are the same at that point. And so that's what we are saying here. The x-coordinate is opposite at that point. The y-coordinate is opposite the original, but these slopes are the same. So hopefully this will be able to help you. Sorry I can't just give you the unit circle for the test, and honestly there's only maybe 2 or 3 questions that are like straight up unit circle on there anyway, but this should help you dramatically for your test. Okay, thanks for watching.